Okay, so good morning, everyone. Welcome to the Rencontres théoriciennes. So this week we're very happy to have Daniele Dorigoni from Durham, but I think live from Berlin. Please tell us about some exact results in n=4 super Yang-Mills theory, please.
Thank you so much, Boris. It's a great pleasure to give this seminar with this audience. Would be extremely happy to be there physically, but these circumstances. So good. I would like to tell you about a couple of works. Well, one is a letter. I would suggest you to read the second one where we put all the gory details that we've been doing together with Michael Green and Konkao Wen. I decided also to give fewer technical details and a longer introduction, but please do interrupt me at any time. So just to set up a little bit the language and what I'm actually talking about, I want first to remind, well, I don't really need to remind too many of you, but it's always good to remind in general, few couple points that we're going to be using. So the main topic is, of course, 4-dimensional n=4 super Yang-Mills with SUN gauge group. So the result that we derived, it's valid for any n. So I'm going to be discussing also the large n theory, but we're going to be discussing for most of the talk finite n. 2, 3, your favorite number. So the first key point that we're going to be using is superconformal formal invariance of n=4. Then I will remind you a little bit about Olive-Montonen electromagnetic duality, which gave us a lot of constraints on this actual correlator that I'm going to be telling you about. And of course, we actually provide functions, so we need to have some computational tool. And this comes from Pestun, SUSY localized partition function. And at the end, I'm going to be drawing also some connections between this type of correlators. And of course, I'm sure that everyone heard about the holographic relation with type 2b on ADS5 cross S5. This in here is when I'm going to be advocating large n. Good. So just to set up a little bit the notation and what I'm actually talking about, let me remind you briefly of a particular class of operators in n=4 super Yang-Mills. So n=4 has a bunch of operators, but there's some special ones which are protected. They don't receive any radiative corrections to their anomalous dimension. In particular, between all the fields, the one I have in mind are the adjoint scalars, phi I, 1 all the way to 6, where this index I is, of course, the SU4 R symmetry index of the SO6. And with these scalars, you can construct this operator O2 at position X and Y, which I'm going to explain in a second, which is given by trace phi I, phi j, yi, yj, where this is just a null polarization vector to soak up these SU4 indices or these SO6 indices. So in most of the following, I'm going to be dropping the R symmetry indices. Whenever there is an index, think that you're multiplying by a polarization vector, so you get rid of that. So these are the so-called 0 to 0 operators, or the 20 prime operators. Whatever it means that is in the symmetric, traceless representation of SU4 R symmetry. The nice thing about these operators is that they are protected. They are a half BPS. So that dimension is 2, period, no corrections. So this, in general, is an extremely powerful result to have whenever you have an operator which is protected, when you can use superconformal invariance to get a lot of constraints. In particular, just for the students in the audience, the 2-point function of such operators is completely fixed by superconformal invariance. It takes the form y1 dot y2, the two polarization vectors dotted, divided by x12 to the fourth power, where x12 is x1 minus x2. So here, there's nothing, no coupling constant dependence, nothing. It's this given function. However, the 4-point function, it is not. The 4-point function of these guys is an extremely interesting object. So O2x1, let me drop, as I said, the R symmetry indices. O2x4 schematically takes the form 1 over x12 to the fourth, 1 over x34 to the fourth, and I said fourth, but brought 2 for some reasons, 4 times a function, let me call it Tn, of u and v, where this n is the n of SUN, and these two guys are the two cross ratios. And I didn't write it out, but I should have. So, well, let me keep it like that. This function in here, this Tn, is non-trivial in the cross ratio, and it is non-trivial in the coupling constant. So this function here, in general, we do not know it. You can analyze it to the bootstrap. There's been a lot of recent progress in here in the study of this particular 4-point function in the larger limit via bootstrap techniques. But in general, we do not know this function explicitly.
Sorry, a simple question. Why you say is a null polarization? Is it complex?
Yes, in general, it's a complex number, exactly. So you want the traceless one, right? So in this way, when you get the traceless part, you just get directly null. Yeah, you're absolutely right. In general, there's some, they're going to be complex polarization vectors. Thank you. Yeah, if you wish, is just a way not to deal with indices. You soak up every SU4 index with one of these polarizations. So at the end of the day, you drop the indices completely. Our symmetry and superconformal invariant tells you which structure. So in here, I bypassed a lot. There's actually 6 different structures with these polarization vectors that appear. Thank you. Good. And the other thing that I wanted to mention about this 4-point function is that this operator O2 is the superconformal primary in the stress energy multiplier. Which means that in principle, you could just act with a bunch of supercharges, superconformal transformation. And if you know this 4-point function, you should be able to say something about the 4-point function of 4 stress energy tensors. And the reason why this is interesting is because, as I'm going to say a little bit towards the end, is that, of course, the stress energy tensor, yeah, the holographic picture is related to the graviton. So knowing this 4-point function tells you about the 4-point graviton amplitudes in time to be. So this is yet another reason why this particular 4-point function is an extremely interesting object to study. So this is just to set up the main guy of our discussion. One of the points that I'm going to be using is, okay, can we actually constrain this object? And this Olive-Montonen duality that I mentioned at the beginning, it's an extremely important tool. So this also allows me to set up a little bit of convention. So this electromagnetic Olive-Montonen duality tells me that this function, Tn of u and v, must have certain properties in regards of its decoupling constant dependence. So just to set up notation, I'm going to be studying n equal to 4 super Yang-Mills, and the coupling constant is easily packaged into a complex coupling constant in which the real part is just the topological theta angle, and the imaginary part is just 4 pi over G Yang-Mills squared. Just in terms of notation, sometimes it's useful to introduce an auxiliary function y, an auxiliary variable y. which is nothing but tau2 times pi. So whenever I'm going to be talking about weak coupling, what I mean is, of course, GM mils going to 0, which is equivalent to this tau2 going to infinity, which is equivalent to y going to infinity. And similarly, whenever I'm going to be talking about strong coupling, I'm going to be meaning GM mils going to infinity, which is equivalent to tau2 going to 0, which is equivalent to y going to 0. With this notation set, what this Olive-Montone duality tells us that there should be an invariance under the following transformation. You take the coupling constant tau and you send it to gamma tau of the form A tau plus B over C tau plus D, with gamma, this matrix A, B, C, D, an SL2Z matrix. In particular, usually the one that we know and we use the most is S duality, for which the matrix is just this one, and acts on tau minus 1 over tau. So if you wish, when the theta angle is 0, this S duality just takes coupling constant and sends it into 1 over the coupling constant. So we expect this observable to be invariant under this SL2Z, Olive-Montone duality group. Yeah.
Isn't there a larger symmetric group GL2Z sending theta to minus theta? Not sure actually.
I don't think, well, the expression that we get is for sure only invariant under SL2Z. So we're going to be writing this as lattice sum. Of course, like, you know, in here, when theta is not 0, this involves theta, of course. But
sure.
Usually you just think it as an inversion of the coupling constant, which is technically true only when theta is equal to 0. But I think the end result is only going to be invariant under SL2Z. Yeah.
Okay.
Yeah. Thank you. Good. So let me just give you the result of our calculation, which I'm going to be sketching later on. But the result is that from SUSY localization, we consider, well, and I mean Pestun, consider n equal to 2 star, which is just a mass deformation of n equal to 4 on a 4 sphere. And we compute the following object: Gn of tau and tau bar is 1 over 4 the Laplacian with respect to the coupling constant, 2 derivative with respect to the mass, the logarithm of Pestun partition function. And then we set the mass to 0. So this delta tau, let me just remind you, is just the SL2Z invariant Laplacian. You compute this object, and thanks to the result of Binder, Chester, Pufu, and Wang, this combination is actually equal to an integral over the 4 insertion points, a certain measure on the space-time. It's super concrete. Let me not just write it down because it would take me a bit longer. And this 4-point correlator I was telling you about before. So localization tells you that if you compute this particular deformation, you get this object. And it's not too difficult to understand that this should have somehow to do with a 4-point function. You see in here, I'm taking 2 derivatives with respect to the coupling constant, 2 derivatives with respect to the mass. So I'm going to bring down whichever operators are attached to the coupling constant and the mass. You need to play a lot with word identities, and these 4 gentlemen in here proved that this is what you get with a very well-defined measure, which depends on the cross ratios.
Okay. Sorry, Daniel, again, just to give us a feeling, why don't you take 4 derivatives with respect to M or tau?
Excellent question. So these people, together with Michael Green and Konkao Wen, consider also that case. And I'm going to mention something about this towards the end. That case is actually turns out to be much more, well, shouldn't say much more. It's on the same spirit, but it's more complicated. Yeah, but you're absolutely right. You can do even more than that. You can consider a squashing of the force sphere. You can take derivative with respect to the squashing. There are some word identities relating a bunch of these different derivatives, but you're absolutely right. You can take 4 derivatives and you get yet another. So the interesting thing is that with 4 derivatives, sorry, I should put a log, then you put the mass equal to 0. You get the same expression with a different measure, but the same 4-point correlator. However, from the point of view of the coupling constant dependence, this case is much more complicated. Yeah. So I'm going to mention something towards the end. Thank you so much for the question.
Is there some regularization involved in performing this integral over the 4 positions?
Good. Not really, because you are on the sphere at the beginning. So 2 of the points can actually be said to be at the north and the south pole. But eventually, when you take the decompactification limit, I don't think any regularization is really required.
I was worried about UV, I mean, about coinciding singularities.
No, there must be something. Of course, from the point of view of the partition function, there is no reason to regularize anything.
Yeah.
But if you want, suppose, to start from the correlator and calculate it and match it to that, of course, then you will have to use some regularization.
Oh, absolutely.
So something is implied.
Yeah.
But unless the measure mu is such that it regularizes or it's integrable against this correlator, that's all.
Yeah, so for sure, if you think it in terms of really taking this 4-point correlator, then definitely what Elias was saying, absolutely. From the point of view of the localized partition function, well, of course, once you localize, that's it, you get a result and it doesn't need to be regulated. But presumably it's automatically inputting some sort of regulator for these coincident points. Because of course, as I was saying, clearly taking derivatives brings down operators, well, not quite, brings down operators integrated over the force sphere. So there could be some points in which the operator go and coincide, but the end result is finite, yeah.
Well, it all depends on this measure mu that you're not displaying, but that's okay.
Yeah, if you want, I wrote it down. It's very simple to write. It just is not particularly illuminating, at least not to me. It is a function of U and V, and you're integrating over U and V, yeah.
Well, the question is that does it vanish at coincident point, I guess?
That is the question.
Well, it does not actually, yeah. But at coincident points, you see, at coincident points, you have the okay. It does in the sense, well, yeah, it should actually, because at coincident points you can actually use the OP for these guys. And you can actually go down to
it has to vanish sufficiently fast.
At least, exactly. Yeah. So let me take back. It does indeed. Yeah.
Okay. Thank you.
Thank you.
Absolutely. A related question.
Oh,
hi. So those authors generalized the story to compute integrated 2-2-PP correlators, where P is the PPS again.
Yeah.
Is the integrated 4-point function PPPP a supersymmetric observable as well?
Oh, that's a good question. It's for sure not in their paper. So this is in their paper.
Yes.
I am actually not sure. Yeah, that's a very good point, because I was giving the same talk yesterday in Durham. So Paul Heslop told me that actually they do know this PPPP imperturbation theory, at least their integrants to some loops. But I'm not sure. So for example, this has actually not been really computed via localization per se. So you can do the same analogy, you can take a bunch of derivatives, but the actual localized partition function has not been computed for these guys. But for 4Ps, I don't even know if that is actually, yeah, that's a good question. Short answer is I don't know. Yeah, thank you. Yeah, no, that's a very good point. OP1, OP2, OP3, OP4. Yeah, thank you. I'll think about that. Good.
Don't you need at least 2 tau derivatives?
Oh, I
can switch on my video. I exist. Well, can you not? Don't you need at least 2 tau derivatives, like a tau and a tau bar derivative, to make this log z?
Oh, sure.
So actual observable.
Yeah. So in here you really consider d tau p, d tau bar p, d2m. But I wonder if something similar you can obtain it. Yeah.
But log z, I mean, you still have the Kähler transformations, right? Which you kind of want to kill with the z tau and the tau bar derivative.
Mm.
And so that would suggest that you need at least a tau and a tau bar derivative. And then to answer Eric's question, I would suspect that you would need at least an O2 insertion to get something that you can compute.
You mean log z is not well defined up to some Kähler deformation?
I thought so.
I guess I can still imagine that. So the question was, is PPPP integrated for some measure? Does there exist a measure for which that is a supersymmetric observable? Now, whether it's related to log z in some way is a separate question. And based on your argument, it seems not. And presumably that's why the original authors didn't compute it. But integrating that correlator against something is something we can do. Is there a supersymmetric choice for that, where then we can figure out later how to actually do it? That was the baseline question.
We should leave that for after the talk and proceed.
Yeah, sure. Well, nice seeing all of you guys, by the way. Good. So let me tell you what we found, actually. So what we found is that this particular integrated correlator can be written in the following form as a lattice sum of an integral transform e to the minus t m plus m tau squared divided by tau2 times some very simple function of this integration variable t only. With this, let me call it Borel transform, takes the form qn of t divided by 1 plus t to the 2n plus 1. And this qn of t is just a degree 2n minus 1 polynomial with integer coefficients. So first of all, one thing that you might ask, and I can tell you already, I don't know the answer to. So whenever you have a polynomial with integer coefficients, chances are you're counting something. I don't know what we're counting in here. This said, with this particular expression, for example, let me give you for SU2, is not particularly ugly polynomials, 9t minus 30t squared plus 9t cubed. One of the key points that we used, and if I have time, I'm going to mention why this is important later on, is that this integram satisfying the following inversion property. But for the moment, this is just a property that I'm telling you. The interesting thing is that, first of all, this expression contains an infinite number of instantons and anti-instantons contribution. So it's non-perturbative, fully non-perturbative. Going back to the question that I was asked before, if I consider D for M, not only you have instanton and anti-instantons, you also have instanton anti-instantons together. And that makes life much more complicated and also much more interesting. Secondly, if you have worked long enough with lattice sums, whenever you have a lattice sums of this type, it's automatically SL to Z invariant. So also going back to Boris, I don't think this is GL2 invariant. I think it's only SL2 invariant.
Sorry, a quick question. Is this relation B and its inverted formula related to the weak or strong coupling asymptotics of this function?
Good. Yes, absolutely. But it's a little bit subtle than that. So
okay, I'll wait.
Yes. So if I have time, I'm going to give you the details. Otherwise, please ask me at the end of the talk, Elias. So you're absolutely right. It's in that direction. But what you're really doing, you're taking the weak coupling of which is just perturbative expansion, but then you're taking the strong coupling of the zero topological sector. So you forget the instantons. You see, instantons are strong coupling. They're not instanton any longer, right? They're not exponentially suppressed. But if you drop them and you study the strong coupling of what is left, this relation is telling you that the two are exactly matched. Yeah. In terms of modular forms, this has just to do with the Weyl invariance. It's just the two terms in the Eisenstein are related by Weyl symmetry. This is the bottom line. But it has to do with what you're saying. Thank you. So good. So to my knowledge, this is the only concrete example for something which is manifestly SL to Z invariant for any SUN. So it really has Olive-Monton duality. And even perhaps more surprising, so we found this expression, and then we found the following corollary, that this expression tells you that there is a Laplace difference equation. Oh, that's a terrible underline. Which is satisfied by this integrated correlator. If you consider the Laplacian minus 2 applied to Gn, this is equal to n squared, the correlator in the n+1 theory, minus twice the correlator in the SUN, plus the correlator in the SUN minus 1 theory, minus n, the correlator in the SUN plus 1 theory, minus the 1 in the SUN minus 1 theory. So this localized correlator satisfies this Laplace difference equation. So as a corollary in particular, if you input in this equation G1, okay, G1 is trivial, is for SU1, so G1 is 0. You put G2, so the SU2 partition, sorry, the SU2 localized correlator, you can solve for every SUN. Another interesting thing that we're going to be using later on is that you can actually take the large n limit of this expression, which reduces to something which is particularly nice. You have a Laplacian in the coupling constant, but you also get a Laplacian in n. So you get this sort of Laplace equation, both in the coupling constant and in n at large n. In particular,
sorry, a question. That looks a little bit like what people called the n renormalization group, that is an equation that relates n to n+1 or something. Do you understand why this is second order in n?
No, yeah.
Okay, thank you.
Yeah. That's a very good point. Yeah. So the way we found this expression is that first we constructed this Bn. Oh, I should have said it, sorry. So we have a very concrete realization for these polynomials. I'm not going to write it in this talk. Can be written in terms of Jacobi polynomials. Jacobi polynomials satisfy a 3-terms relation. This is why we get this 3-terms relation in here. Yeah. But this is the mathematics. I don't understand the physics behind. Yeah. Thank you. An alternative form, so sorry, I should have also mentioned, this object that I wrote in here, this is a function. So in the upper half plane, for tau belonging to the upper half plane, this is a convergent integral and a convergent lattice sum. So this really defines for you a function, a modular function in the upper half plane. However, there is a sort of suggestive way to rewrite it as an infinite series of Eisenstein series. So you can write the same object as n-1/8 plus an infinite sum of some rational coefficients which depend on n times the Eisenstein series, the non-holomorphic Eisenstein series. I think there is a half in here, it doesn't matter, because I'm not telling you these numbers, but we have some very concrete realization for these numbers. And maybe for the people in the audience who have not worked with them, in general, you can write this. Has a lattice sum, of course, again, tau 2 to the s divided by m plus m tau to the 2s. And I think I'm forgetting some factor of pi to the s. This is a modular function solution to the following Laplace equation. However, these coefficients Cns are factorially growing. So this is, if you wish, it's a formal way of writing this function in here. The reason why I wrote it in this way is because you see in here that this index S appearing in here is an integer. However, from the expression here, we can also extract the large n limit. And in the large n limit, the story changes dramatically. At large n, we can get a very similar expansion of this object. Now you get an asymptotic expansion in 1 over n. There is a constant term n squared over 4, which is actually physically important. And then an infinite sum over half integers power of n, and a finite sum over half integer Eisensteins.
So that's not the Toft large n limit, right? You keep.
No, it's not. Thank you. Thank you so much. I was going to write it in a second. You're absolutely right. This is not the Toft limit. The reason is that we keep tau fixed as n goes to infinity. So remember, tau contains the coupling constant. We are not scaling it. The reason why is only in this limit that you hope to make connections with type 2b. And these objects in here, which are appearing, these half integer Eisensteins, have actually been computed in type 2b as coming from some higher derivative corrections to supergravity. So over there, it was crucial that you were not in the Toft limit. You really have tau related to the axiodilaton, the string coupling constant, if you wish, and it's finite. And Green and other people, Van Hove and friends, have computed a lot of these 1 over n corrections, 1 over root n corrections, and they come in half integer Eisenstein. So I'm going to make
sorry, Daniele, but I thought that the holographic duality is relating the Toft limit to type 2b, right?
That's good. So that's yet another thing that I'm going to be giving you in a second. You can also study the Toft large n limit. However, over there, you lose modularity. In the Toft large n limit, you only have a function of n and the Toft coupling. So theta is gone. And you can get a genus expansion that, of course, it contains the stringy corrections. However, if you take this non-Toft large n limit, where tau is kept fixed, you can actually map this tau to the axial. So in this case, tau, you should really think it has chi plus I over G string. And at this point, you can think about studying type 2b. Well, really what you would like to do is study type 2b in flat space. So there are some issues in here because we are not really in flat space. You would really get it on ADS5 plus S5. But if you study the stringy corrections to supergravity, you will find this 1 over n, which is really an expansion in alpha prime at this point. And tau, it's really the coupling, the string coupling.
Do you mean 2b in flat space or 2b with the stack of n d3 branes in flat space?
Oh, well, probably the second, right? Yeah. Yeah. Good.
One more question.
Yeah, absolutely.
Sorry, can you say again what the convergence properties are of the original object?
Good, thank you. Okay, so this object in here.
Yes.
Well, let me write it in here. So convergence. So let me write it again schematically. We have a lattice sum and an integral. Phi m plus n tau squared over tau 2, and then this function. Good. So this function in here is vanishing at the origin. So you don't have, it goes like order t at the origin. And it actually goes like order t minus 2 at infinity. So for fixed m and n, and tau in the upper half plane, each single integral is defining for you an analytic function in the upper half plane. Furthermore, you can actually study the behavior for large exponent. So you might worry about the lattice sum, but for large exponent, this integral goes like 1 over m plus n tau to the 4. So the lattice sum is convergent. Said differently, I did numerics. We put a couple of plots. I produced much more. The story is actually interesting. So since you asked me, I can tell you a bit more, especially because Balt did some work on something, well, not really related, but good. So we are in the upper half plane. And these are the 3 fixed points. So this is I, and S of tau is equal to tau in this case. This is e to the I pi 3, and this is e to the 2 pi I over 3. And these are fixed under ST. So these are some of the fixed points under a part of SL2. What happens is that this is a saddle. These two are max, and the cusp, which is also dual to 0. This is the only minimum of this observable.
This was for n equal 2 or something like that.
Oh, for any n, yeah. So the numerics that I produce in the paper is for n equal to 2, but we can do it for any finite n. Yeah. Yes, yes. Good. However, going back to your question, Eric, this expression in here means very little because these coefficients are factorially growing. And secondly, you see, this is not even a power series because this Eisenstein, so I should have written it here. So this Eisenstein goes like some zeta even, y to the s, plus some zeta odd, y to the 1 minus s. And remember, this y is
in your notation.
Good. So the reason why I wrote it like this is because you forget factors of pi. So y is pi tau 2. Yeah.
Sure.
So this is inverse coupling. So you see that this is a strong coupling term, and this is a weak coupling term. So this expansion means very little. However, that's actually the way we found the full expression. So in here, I shouldn't really write equal. The right-hand side is not defined. It's defined as the integral transform that I wrote above. But the integral transform that I wrote is a function.
I see. Part of the reason I was asking was to understand whether it was an L2, in which case it admits a decomposition into Eisensteins in the principal series. And then you can deform the contour to write it like this sometimes, but maybe the other representation is more natural from the SL2Z perspective. And I was wondering if it admits that and if you can the overlap.
Yeah, we have not done that. Yeah, that's a very good point. Yeah, so this object in here is perfectly good. This expansion in here is not really. Yeah, absolutely. Thank you. Good. So the point that I wanted to make in here is that for any finite n, you have an expansion in integer Eisenstein. For infinite n, you have an expansion in half integer Eisenstein. You have this sort of transition between the two. So good. Given time, rather than giving you the details, I would be happy to giving you some more details on how we computed this stuff. But let me give you some of the checks and the consequences of this particular expression. Okay, so first of all, let me just use some notation. So we decompose this function in general in Fourier modes. So as I said before, there are instantons and there are anti-instantons. So we just do a Fourier mode decomposition using tau 1, which is the theta angle, as our parameter. So it takes the form e to the 2 pi I k tau 1, and then a Fourier mode that depends only on tau 2. And remember, this object in here is nothing but e to the I theta k. So I would say k bigger than 0 are the instantons, k smaller than 0 are the anti-instanton, k equal to 0 is perturbation theory. Again, I can say this because in this case, we don't have any instanton anti-instantons. D for M is much more interesting because in the zero topological sectors, you also have instanton anti-instantons objects. Okay, so with this in mind, what are the checks and the predictions that we can do? Well, there's quite a lot of them, and we can explore a lot of different regimes. So perhaps the first that we should check is small GM mills and fixed N. This is just super young mills perturbation theory. Then you can go into large N fixed toothed coupling, which is something that we were discussing before. And this is literally toothed ligament. And finally, large N fixed tau. And this is the limit that is going to make connection with these 4 graviton amplitudes. So let me start with the first. So here we want to make connection with super young mills perturbation theory. From our expression in here, from this integral transform, we can actually compute order by order in GM mills. So let me just focus, as I said, on the zero topological sector, so perturbation theory. Everything is just a function of GM mills. However, let me not quite use GM mills. Let me write a new coordinate A, which I'm going to be, well, let me write in here. A is the would-be toothed coupling, is GM mills squared, N over 4 pi squared. However, remember in here, N is fixed to your favorite value, okay? So it's not toothed limit. It's just a compact way of writing what I'm going to write in a second. In this way, you get the following expression, N squared minus 1 times, and now I need to write some numbers, but bear with me for a second, 3 zeta 3 over 2a minus 75 over 8 zeta 5 a squared plus 735 over 16 zeta 7 a cubed plus, actually it's a minus 6615 over 32 zeta 9 a 4, 1 plus 2 over 7 n to the minus 2 plus order a to the 5th. So the reason why I wanted to write some numbers is, first of all, there are only odd zeta values appearing in here. So this is perturbative expansion. We only get odd zeta values of the maximal transcendentality. Secondly, you see that apart from this factor n squared minus 1 and the n hidden inside A, the first 3 loops are n independent. So you see that there is no appearance, just 3 zeta 3 over 2, 75 over 8 zeta 5, and that number over there, zeta 7. So this is actually something that was already expected from perturbation theory. So this correlator should not receive any non-planar correction up to 3 loops. The thing that we did, and in here I should say, the thing that Concow did, is you can actually, this correlator O2, 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 O2 is known in perturbation theory. There is actually a really nice work by James Drummond. Aiden, Paul, not Pennington, Pennington. And I'm missing someone, Spindler, which are telling you what this correlator is in 3 loops. Well, we know the 1 loop, the 2 loops. So what you can actually do, you can take this correlator unintegrated. At 1 and 2 loops, only ladder diagram contributes. You can integrate against the measure that I did not tell you, and you find these first 2 numbers. We did not do the 3 loops because although, as I said, these people in here told us what the correlator unintegrated is at 3 loops, is a mess. It contains all these Goncharov polylogs, so we weren't even sure how to actually implement numerics in Mathematica. But in principle, you should take this unintegrated correlator, integrate it against the measure, and you're going to find these first 3 numbers. At order 4 loops, you start receiving non-planar correction. So you see this 1 over n to the minus 2. And then you have an interesting pattern. At 5 loops, you only get 1 non-planar correction. And then at 6 and 7 loops, you get 2 non-planar corrections. 8 and 9, 3 non-planar corrections, sorry, 4, and then so on. So it jumps in steps of 2. But at least the perturbative Yang-Mills expansion of our correlator, you can actually get it from proper perturbation theory. Second, which is something that I did not touch before, is the 't Hooft-Largen limit. So we now fix G Yang-Mills squared times m. And this is where the story starts becoming interesting. At this point, the instantons are gone. We lose modularity. We only get the purely perturbative part, which we can expand in a genus expansion. Which again, in here, I shouldn't write equal because I expect this object to be an asymptotic series. From the expansion that I just wrote above, it's very simple to read the planar correction, the non-planar correction, genus 1, the non-planar correction, G2, and so on. So let me just focus for concreteness on the planar one, which we can actually write in a very concrete way. And again, we only get odd zeta values, multiplying rational numbers. They don't look rational, but trust me that if you plug in all these numbers, well, it's not difficult to see given the gamma factors. So this is actually rational. Lambda to the n. This object is convergent at weak coupling. So the 't Hooft-Largen limit gives you a convergent expansion at weak coupling. I just wrote you the planar one. This is true for all the higher ones. We can actually rewrite it in an integral transform. The only reason why I'm writing it is because if you have worked in integrability, you will recognize these sort of kernels, which are product of 2 Bessel functions divided by some sinh. So this had already been obtained by Chichester and Pufu. And it's the resummation of this perturbative expansion. However, we can also expand it as strong 't Hooft coupling. What we find as strong 't Hooft coupling is that the theory is actually giving you an asymptotic expansion at strong coupling. Where are my details? Oh, perfect. Yeah. So as I said, this matches what has been found by Chichester and C.B. Pufu. The strong coupling is asymptotic, but not Borel summable. So if we take this expression and expand it at large n, we find that we need to supplement it with an infinite number of non-perturbative corrections. So in here again, let me just write 2n plus 1 factorial. I put quote unquote because it's a gamma, there's a bunch of factors, but it morally goes like 2n plus 1 factorial, zeta 2n plus 1 divided by square root of lambda, the 2n plus 1. Using resurgence method, we were able to supplement, as I said, this asymptotic non-Borel summable series to define the proper analytic continuation, which corresponds to this integral in here. And the non-perturbative terms are of this type. 2.7, okay, to the date, doesn't really matter. And then you start getting polylogs plus some other number, Li1, divided by lambda to the half, and so on. So these non-perturbative terms, well, first of all, I say that they're non-perturbative, and the reason is that this object in here goes like e to the minus 2 root n plus e to the minus 4 root n plus e to the minus 6 root n, and so on. So this one can be thought as having resummed all the instantons at 3 level, all the instantons at 1 loop, and so on. And sorry, I should not call them instanton. I should just call them non-perturbative objects. They're not instant of n equal to 4 for sure. What are these objects? Well, if we now reinstate the various stringy quantities, these guys go like exponential of -2 L squared over alpha prime, where alpha prime is, of course, the string length square. And L is the ADS scale.
So these are worldsheet instantons?
I was going to write it next. Thank you. Spoiler, as Elias said, these are indeed worldsheet instantons. Indeed, and we can retrieve them from the finite and expanded in this two limit. Good. These are very similar to actually some.
Sorry, in one sense.
Sorry, I couldn't hear.
In what sense are they worldsheet instantons? I mean, there are no two cycles.
Oh,
it's 5 causes 5. So can you say it?
Good, excellent question. So this connects with what I was saying before. So morally, they behave like worldsheet instantons. We found very similar objects with Glebary tune of any students gave when we were studying the dressing phase of n equal to 4. And that one is not the cusp anomaly. So you have similar objects, but they are further suppressed in the cusp anomaly. And in the cusp anomaly, you know what they are. They have to do with the underlying O6 sigma model. I think Benjamin is in the audience, so Benjamin has worked on that. In this case, in the case of the dressing phase, or in this case in here, it's not really clear. I do not have a semi-classical configuration with this action, because precisely what you said. But there should be something which is maybe like unstable in the sense of spheron. So I can say the following. The difference between these non-perturbative objects and the non-perturbative objects that Benjamin has found is a factor of 4. And 4 is exactly the second Casimir of O6 and n-2, which is 4. This difference suggests that in that case, they are non-perturbative effect of the O6 sigma model, like the O6 sigma model mass gap. These guys are 4 times as big, and they should be some sort of spheron-like configuration. These are a lot of words to say, I do not have a semi-classical realization of this. Yeah. Okay. Thank you. Good.
Daniele?
Yeah.
This expression is a function of lambda. So the extension of the non-convergent first line by the second line.
Yeah.
That allows us to access what range of lambda?
Oh, good. Excellent question. So in here, everything I'm writing is what is called a formal trans-series. This is still an asymptotically growing object. And in here, I'm putting this plus or minus, which is called the Stokes parameter. I can resum it in an integral transform, which allows you to explore the full complex lambda plane. Minus, there are 2 cuts. So at the end of the day, this object is defined in here. This is the complex lambda plane. You have a branch cut that ends at I pi and at minus I pi. Here is the realm of weak tooth coupling limit, which is convergent. All the way here is the realm of strong coupling asymptotically factorially growing series. But at the end of the day, this function is defined on this cut complex plane. Thank you.
Thanks. And it's always classical polylogs?
Yes, exactly. Yeah. So we did it also for G1, the first non-planar correction. It a little bit more complicated, but they're still just classical polylogs. Yeah.
Thanks.
Good. And the final thing that I wanted to mention, and then I can conclude, is the final regime, the regime of large n fixed tau. And we can conclude in here because then we can discuss a little bit more. So the expression, again, that I gave you before, this integral representation, although I didn't write Bn, this is a very simple function. It can be written in terms of these Jacobi polynomials. In particular, I can expand it at large n. And at large n, this object behaves in this way. N to the half, t to the half, plus t to the minus 3 half, plus s to the minus a half, to the 3 halves, plus t to the minus 5 halves. And then in here it gets a little bit more complicated, n to the minus 3 halves. And you have 2 sets of terms, t to the 5 halves, plus t to the minus 7/2 plus some other number, t to the half plus t to the minus 3/2, and so on. So this is the expansion of this function that I didn't write you, but it's very concrete. You can write it in terms of hypergeometric functions if you wish. But remember that the Eisenstein series can actually be written as the lattice sum that I wrote before, but then we can just exponentiate it using Schwinger parameter trick. T to the s minus 1 over gamma s. So you see that once I give you an expression of this form, you see that you get exactly a term of this type. The only thing that you need to be careful is that there is this shift minus 1. So t to the half corresponds to e3/2. This object in here is just the mirror one. So there is this identity that es gamma s is equal to e1 minus s gamma 1 minus s. So that is just the flip term. So at large n, we find that this integrated correlator is still modular invariant. It has a constant term n squared divided by 4, and then it starts having an expansion in half integer Eisensteins. So this expansion had already been found by Green, Fufu, Chester, Wang, Kao, and I think I'm missing someone, and Binder. Good, let me write this last term. So you get an expansion in half integer powers, and it reproduces and extends this work that I was saying by Chester, Green, Fufu, Wang, and Wang. Again, the Laplace equation kind of forces it upon you. I didn't tell you why, but if you plug in an half integer in n expansion, the Laplace equation tells you, no way, you need to have half integer Eisenstein.
Sorry,
now,
this Eisenstein series,
we can make...
Excuse me, can you match this Eisenstein series to the coefficients of the four graviton coupling?
Can you hear me? Yeah.
Yeah. Can you match this?
Yes, I can hear you now, Boris, sorry.
With the coefficients of the R to the 4 and higher derivative couplings in
Yes, this is what I was going to write now. Thank you. Absolutely.
Sorry.
Almost. You can write. So you see, the fact is that the one that you have in mind are the flat space limit. Yeah. You need to pass through this Mellin transform and then take the flattened limit of the Mellin transform to get to the amplitudes. You can get some of the coefficient. For example, the D6R4, it's completely missing here. So this is what I wanted to write next, and I conclude in here. So from type 2b, the coupling constant is this one. So SL to Z is really S duality, or in general, U duality whenever you study compactifications. And the 4 graviton amplitude can be expanded in a low energy expansion of higher and higher derivative corrections. So you start with supergravity. And if you do all the things carefully, supergravity is multiplied by alpha prime to the minus 4. This object translates to n squared, which is this guy here, which is, of course, it's modular, is a constant, but it's a little bit trivial. And then you have these higher derivative corrections. The first one is R to the 4, as Boris was asking. This is multiplied by alpha prime to the minus 1, which corresponds to square root of n. This guy in here is exactly that contribution. Then the story starts getting a little bit murkier, because you have D4R4 and D6R4 and so on. So this is alpha prime. This becomes 1 over root 10. This is alpha prime squared, and this is 1 over n. So you see here that I don't have any 1 over n. For this, you need to study this other correlator that I was telling you about. So Chester, Green, Fufu, Wang. And Wang studied this D4M at large n only. And this guy contains 1 over n times this, let me use their notation, and something that they call E3/3, which is exactly this coefficient of D6R4 that Michael van Hove studied a long time ago from superstrings. So you get a few informations about these higher derivative corrections. It gets a little bit trickier. So I should say the reason why I stopped in here is this is the last BPS operator, the last BPS protected operator.
Sorry, do I understand that the integrals that you do for the correlation function miss some information about the 4-point correlation function? So you have to
Yeah, because you're doing an integral, right? So you're somehow projecting onto some slicing, and then you want to extract the then you want to extract the flat space limit. So you don't have full control over the higher derivative corrections, yeah. But even more so, the reason why I stopped in here is that this is the last BPS protected operator. However, then after that, you still have like higher derivative corrections. And people studied, so all of these higher derivative corrections, they are multiplied by a function of tau, and this is a modular function. And for all of the guys I wrote in here, this function satisfies some Laplace-like equation that allows you to fix this coefficient. And this Laplace equation is crucial that it comes from supersymmetry. After that, supersymmetry doesn't help you anymore because the operators after that, they're not BPS anymore. However, there's been some proposal in the literature about Laplace-like equations satisfy these higher derivative corrections. I don't want to comment on that because I don't think there should be any. They're not protected, whatever. However, in our expansion, you get higher and higher terms in 1/n. So you could ask, what are they really capturing? Are they capturing part of the story, the full story? For that, I really don't know. So we see that the first few, you can actually match them, but higher, it gets a little bit trickier. And also, you don't really get the full story, precisely because I was saying, we don't get the full correlator, right? We're getting an integrated version, and this somehow loses some information after a certain stage. So let me stop in here and let me just say a couple of open questions. Well, first of all, as I just mentioned, this D4M of Zn, this contains also instanton anti-instantons objects, which I find them really interesting because I was coming from resurgence part, and the resurgence part really cares about these non-perturbative terms and how to read them from perturbative expansion. So this tells you that Eisensteins are not enough. Eisenstein are not enough. You need to use something slightly more general. This what they call generalized Eisensteins. Modular graph functions, for the people in the audience who know that, they're of the same spirit. So what are these objects? So I should say in this paper by Chester and collaborators, they study only the large N limit. You have, of course, you still have Peston localized partition function, and you can get some hint from there, but the story is much more complicated there. And another thing that I particularly care is that in all these large N expansions, the large N expansion itself should be asymptotic in N. So for example, N to the 2 minus 2G, or I think I call it G, but whatever. This one is an asymptotic expansion in N. So you should expect exponentially suppressed corrections of this form. We have not explored this part. And similar for the other large N expansion, the large N expansion in half integer powers and these functions of tau and tau bar. So you expect again some exponentially suppressed correction with some modular function now, function of tau and tau bar. And finally, a little bit more like, if you want, okay, all these proposals for this integral version, the Laplace difference equations are all beautiful. We get these integer polynomials. Where are they coming from? Is there some geometric origin behind? For example, as I was saying, this polynomial with integer coefficients. Is it counting something? Or this Laplace difference equation? Yeah, so these are some of the open questions that I wanted to stress because everything we found seems very consistent. I think it's a beautiful picture, especially this Laplace difference equation. We would like to understand it a bit better from a geometric point of view. So let me stop in here. Thank you so much for your attention.
Okay, thank you very much. You can unmute and clap if you like. I clap. And now I will still leave the recording on, and we can take further questions, and then we can go for extended discussion afterwards. So are there any questions?
Can I come back to something I asked earlier? So you got this difference equation for this object in N.
Mm-hmm. Yeah.
As I mentioned, people thought in the past that if you have some theory with N being a parameter, in principle, you can implement some type of normalization group in N. The idea being that you have, let's say, a matrix which is N by N, you integrate out a row and a column, and if this is reasonable, which means these degrees are not massless, etc., you should define some effective theory for a matrix which has N1 less. And this is what would indicate that you will get some sort of evolution equation in N. Now, I was wondering what this result means from this point of view. I would suspect that, of course, the fields you're integrating out in Yang-Mills are not massless, so are not massive. Therefore, this type of doing it wouldn't probably make sense. But what would be the if you wanted to think of this in that way, what would be this interpretation?
Good. No, but I think actually what you say makes a lot of sense, because remember, we are actually studying a massive deformation. So I wrote some details on the localized partition function, but then removed them from the talk at the moment. So let me be a little bit more specific about this partition function. As you said, it's exactly a matrix model. So after SUSY localization, you localize on a particular simple set of constant fields. They are just the zero mode of some adjoint scalar. And the integral takes this form. It's an integral over n variables, subject to the constraint that, of course, they were coming from a traceless matrix, so the sum of them is 0. Then you have the on-shell action, which is just this expression, sum over I AI squared. And then you have what I would call the one-loop determinant, which is a function of these guys and the mass parameter, where Aij is Ai minus Aj. And in a certain sense that you can make really concrete. So after you localize on the fourth sphere, you deform the action by this Q exact term, you get some new quadratic fluctuations, and you can really write an expansion as an infinite product over eigenvalues of this modified Laplacian on the fourth sphere. However, these are not massless because this mass term actually gives them a little bit of a mass. So you can quite literally write it as a product of determinants, an infinite product of determinants. So I suspect that, sorry, I forgot a key piece that I don't think it matters. Well, it does matter for the full story, but not for what we were saying right now, which is Nekrasov partition function, of course. But this is the part that contains the instantons. This is the part that you were probably referring to. So in here, you have really the modes that are surviving in this matrix model, which behave really like massive modes. Of course, we want to take the derivative with respect to m and send m to 0. But what you're saying is very suggestive. So because this is quite literally a matrix model, and you're exactly saying, well, I'm integrating out one of these guys. However, the thing I don't see is how this would connect with the derivative with respect to the coupling constant. But probably this is this RG flow equation type of equation that you were mentioning about, Elias, right? That somehow when you do the RG flow, not only n, well, I mean, you have the whole Kalan semantic type of equation. But
Sorry, I was talking about the RG flow in the n direction. That's
absolutely.
Not the usual one.
Yeah.
The fact that you get an equation that connects the two is, of course, maybe not surprising. It's maybe unusual, but it may have to do something about what these things are from the point of view of string theory. It's something that certainly should be related to some extended duality, because after all, on one hand, you have the coupling constant on which you have SL2Z, on the other hand, you have N. But when you dualize to go to the string theory, N will become the string coupling, and then tau will become some modulus.
Yeah.
And we know sort of similar looking examples in string theory where dualities interchange one with the other. When you go from type 2 to heterotic. So it doesn't look particularly exotic, but certainly if that could be understood, of course, it would be better.
Yeah, absolutely, absolutely. So that's a very good point, because I was trying to understand it more just from the field theory point of view, but perhaps you're right. Perhaps the best way to look at the geometric origin is to go to the string theory and understand a little bit the interplay between n and the coupling constant. That's true, yeah. I should say so we are struggling quite a lot to get something similar for this D4M object. It looks like the first part of the equation remains the same, but it must be supplemented by something else that at the moment we are missing. But it looks like something similar should hold for the full story. Thank you.
Any other question?
Maybe yes, coming back to the type 2b flat limit, do we understand correctly that in the R goes to in the radius goes to infinity limit, the two terms that remain of your computation are R4 and D4R4, and all the one would drop out as being subleading in the
exactly. So in particular, so this was done in this paper by Michael Green, Wen, and collaborators. They did it for both cases. So in here I presented the story for this D2M, but they also did it for the D4M. And actually, if you want, I can, since I have the paper here with me, everyone is working from home and my table is now a mess of papers, but at least I have the right one. And over there, the story is similar, but more complicated. So if you take this D4M of this log, and you set n to 0, you get again supergravity part. In this case, you also get this E3 halves. Then
they are not excluding each other. It's
no, exactly, yeah. But then you get this guy that was completely missing from ours, which is this E, what I call three halves of tau and tau bar. So this, whatever this is, let me call it F because I don't want to keep on writing it. So this of delta minus 12 F equal to E3 half squared. This is exactly the Laplace, the inhomogeneous Laplace difference equation satisfied by the D6R4.
And yet again, now, the other would be vanishing at in the flat limit.
Or subleading, yeah, exactly. It's
so
very tricky.
It's suggestive that you find the same functions, but is there a precise derivation of the coefficient in front, starting from type 2b supergravity?
Or? Oh, for this one, yes. This was Green and Van Hoek, I think, right?
Okay.
Yeah. Yes. But they were doing, you see, so that is completely different, right?
I'm talking about comparison. I'm talking about the comparison with this integrated correlator.
Oh no, then yes, then it's in this paper by Fu Chester. Yes, where they really take the localized this one. You take the flat space limit and you identify the same term. Sorry, I thought you meant from the stringy point of view. That was some time ago. Yeah, of course.
Thank you.
Welcome.
May I ask a very naive question?
Yeah.
About your remark about integrality properties of your coefficients of Qn, of course, you allow for negative ones. In fact, for Q2, there was one negative coefficient. Is there any reason? This is possible in supersymmetric theories, superindices as well.
Yeah.
But sometimes negative coefficients are dropped or disappear if you take the inverse. Now, if I look at your expression, Qn is divided by 1 plus t to something.
Yeah.
So the denominator expression has positive coefficients. So how about 1 over Qn?
I see. So you're saying, sorry, let me rewrite. So the Borel transform takes this particular form. Okay, 20 plus 1. And sorry, one thing that I didn't mention, but since you asked, so this Qn not only has integer coefficient, but it's also palindromic in the following sense. Yeah. It's A0 t to the first power plus A1 t squared plus ... plus A1 t to the 2n minus 2 plus A0 t to the 2n minus 1. So it has this sort of structure. These coefficients are with sign. This structure in here, it's crucial to have this property that I mentioned. that when you invert T, you get back to yourself. But now you're saying something different. You're saying consider 1 over Qn.
Yes.
Ooh, that I didn't do.
It's not a polynomial anymore, but think of 1.
But then you can expand it, yeah.
1 minus T, you take the inverse, it becomes positive.
Of course. Yeah. That's a good question. I've not played with that. Yeah. If they because you see, if I remember correctly, you have basically this alternating in sign. So A0 is positive, A1 is negative, A2 is positive, A3 is negative. So I'm not sure if inverting all of them become positive. But as you said before, when I say counting, I should say counting with sign. Perhaps this object is something like some sum of some character -1 to some fermion number, and then the degeneration of this character.
Okay.
I try to play with this, and when I say play, I mean I took these integers, I compute some of these, I put them on the online encyclopedia for integer sequences, and I hope for the best. And the answer is I didn't find anything, but I've not played with this one. Yeah.
Well, how complete is the Wikipedia which about string theory indices?
Okay.
Yeah.
So getting a little late, I suggest we close the discussion.
Just another question, if possible.
Last, and then we move to further discussions afterwards. But okay, go ahead.
What would happen if you introduced the Nekrasov equivariant parameters epsilon1, epsilon2? Would you expect that some of the structure would remain? And also, are there any other examples where this kind of localization calculation can be rewritten in terms of Eisenstein series? I thought that probably there are.
Not that I know of. So I would be curious if you know of some reference. I would be curious to
I'm not sure. I need to look it up.
Yeah. For the first part with the Nekrasov parameter, that's an excellent question. We did not do that. So I wouldn't even know what the consequences from the stringy point of view are. I'm not even sure if this structure. So you see, even setting epsilon1, the true omega deformation to 0, the higher derivative that still correspond to 4-point function, it becomes more complicated. So you need to allow yourself for more general functions. Introducing those parameters, I don't really know what it would do. So let me think for a second.
I just mean concerning the structure, just literally the same quantity, d tau bar.
Yeah.
And could you rewrite it in some nice way?
Yeah, that's a very good question. Yeah, we have not played a lot with this other deformation. We went directly straight ahead for the D4M, precisely because of the connection with string theory. But that's a very good point. Yeah.
Okay. Very well.
Thank you.
Okay, so let's thank Daniele again.
Thank you so much.
And I will stop the recording if I manage to.